I'm Kristin Burmeister. I'm working at the Scottish Association for Marine Science and I'm a postdoc, so I'm investigating ocean currents in the Atlantic, and those ocean currents have a climate impact. So in July we will deploy this very instrument here next to EB1, the mooring is called, next to our eastern boundary mooring. And colleagues from AF, they will go in August to the western side and deploy the second unit there. The Fetch AZA, it will help us to do the measurements of the long-term AMOC changes more sustainable. So at the moment, as we don't have those drift-free measurements of bottom pressure before, we needed a quite complex array of moorings. You can see that here. This is the OSNAP array in the subpolar North Atlantic. Here you see Greenland, here you see the tip of UK, Ireland, and here you see Canada. And at the moment what we are doing in order to get measurements of the Atlantic Meridional Overturning Circulation in that area is we have around 40 moorings with measurement instrument on them, and they measure temperature, salinity and currents. We also have glider deployments that are measuring the areas in high fishing areas where the moorings are often catched away, so we send our gliders to measure there. And all those data is then used to construct the transport of the Atlantic Meridional Overturning Circulation. So it's quite a complex international approach and associated with a lot of cruises. So what we hope is that with these new bottom pressure measurements, we will drop it on either side of the Atlantic, and then we only need a few moorings on either side to estimate the strong boundary currents, because they are difficult to see in the bottom pressure sensor. But they can be covered with just a few moorings, and all the rest will then be just estimated by the bottom pressure sensors. And furthermore, if we are looking into the future, it might be possible that we don't even need a ship in order to get the data from the AZA Fetch, but basically use the unmanned water vehicle, like for example a wave glider or a glider, in order to retrieve the data, which would then again make the measurements more sustainable and even reduce the CO2 emissions due to the ocean vessels that we are currently using to do all these measurements, which would be great. So the AMOC, the Atlantic Meridional Overturning Circulation, is a big circulation in the Atlantic Ocean, and it's in its upper part it's bringing warm water from the tropics all across towards the north into the Nordic Sea, and this heat that it is transporting is released in the higher latitudes, so in the subpolar North Atlantic and in the Nordic Seas, into the atmosphere, and it warming the atmosphere here. This is why we have this warm, mild and wet weather in Europe. And in the Nordic Seas and in the subpolar North Atlantic, the water masses cool down and they are thinking, and then these cool water masses are brought back through the entire Atlantic towards the south. So it's like a conveyor belt. It's transporting heat and salinity through the Atlantic Ocean, and because of its impact on the atmosphere, it plays an important role for our climate. And when just tiny changes in this circulation can impact actually our climate we experience in Europe and in the surrounding continents. This is why we are studying it. So we are using the Fetch AZA for measuring bottom pressure at the seabed. And we not only have one instrument, but actually we're putting two instruments on either side of the Atlantic. Both are measuring the bottom sensor, And from these bottom pressure measurements, we can then derive the transport that is going from south to north between those two sensors, and we can relate variability of the currents just using bottom pressure measurements. And this is a quite nice and simplified method to identify changes in the ocean current, in the AMOC. Every movement or every ocean current is in geostrophic balance, and that's a balance between the Coriolis force of the Earth. This is something that we explore because of the rotation of the Earth, and actual pressure changes. And we know that from the daily weather forecast and the atmosphere. So you might have seen during a weather forecast that if you have two pressure systems, a low and a high pressure system, when the difference between is strong, so when you have a strong high and a strong low, you have really strong wind in between these weather systems, and what's happening in the atmosphere that is also happening in the ocean currents. And through the measurements of the pressure, we can then relate that actually to the velocity that is going in between those 2 points of pressure measurements. And the stronger the difference, the stronger the current, basically. Before, we had bottom pressure measurements in the Atlantic. However, the sensors that had a large drift, and we were not able to identify this unique drift and the long-term changes of the ocean circulation as due to the drift. It's really individual to each measurement, so you always needed to have a fit. So basically we only could look at variability that were on a shorter time period than the actual measurement period. And those sensors could only be in the water for maybe 1 or 2 years, and then we need to exchange them. So what we are interested in is the long-term change, and the nice one here is that those instruments can stay in the water undisturbed for 10 years, and we only need to pass by basically and downloading the data via an acoustic modem. And so they will sit there for 10 years in the water column, and furthermore we are measuring the drift, the individual drift of the sensor, so we know exactly how they are drifting, and we can remove that, so we have drift-free bottom pressure measurements, and that will help us actually to identify long-term changes in the Atlantic Meridional Overturning Circulation.